Welcome to question 5 of the 2019 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. For question 5, we have the function f with a domain of all real numbers excluding 1, where f of x rule is 2 divided by x subtract 1 squared plus 1. For part 1 of part A, we just want to evaluate f of negative 1. So f of negative 1 is going to equal, and we're just going to take our rule 2 divided by x take 1 squared, but wherever there's an x we're going to replace it with negative 1, so we'll have negative 1 take 1 squared on the bottom line, and then we add 1 to it. That's the same as 2 divided by, and this will be negative 2 squared, which will actually give positive 4, and then we still have our plus 1. So essentially we've just got a half plus 1 is going to give 3 on 2. So that is going to be the value of f of negative 1. From the examiner's report we can see that 93% of students got that question correct, and that overall it was well done in this exam. For part 2 of part A, we're asked to sketch the graph of f on the axis below, and the instruction is then to label all asymptotes with their equations. So before we actually get to sketching this graph, I just want to have a think about what the graph actually is. And this, in its most basic form, would be called a truncus graph. And that's because we'd have a 1 on x squared appearing, and here it's just been translated and dilated as well. So the truncus graph actually has two asymptotes, and the first asymptote is when the bottom line would be equal to 0, which is when x would equal positive 1. And we can see in the domain they've actually already excluded that value, so that gives us a hint that the asymptote is at x equaling 1. So I'm going to draw that first. So using a ruler, we'd put a straight dotted line straight down the page where x is equal to 1, and we need to label that with an equation. The next asymptote is a result of this translation here, which takes the graph 1 unit in the positive y direction. So that means that we're going to have an asymptote at y equals 1. So again, using a ruler, we put a straight dotted line horizontally, and its rule is y equals 1. Next, even though it doesn't ask us to label this point, it's still important for us to find the y-intercept of this graph. So the y-intercept occurs when x is equal to 0 in the rule. So therefore, we're really just evaluating f of 0, which will equal 2 divided by 0 subtract 1 squared on the bottom line, plus 1. So evaluating that, we'll just have 2 over negative 1 squared, which is just 2 over positive 1 now. Then we add 1 to that, and that's just going to equal 3. So we know that the graph will pass through that point there, and because a truncus graph is symmetric, we know that the graph will also pass through the point that is 2, 3. So it's equally spaced from that asymptote. And the thing to note here is that VCAA have provided a grid intentionally, because they expect a good level of accuracy for our graph. So the other thing that we can do is we can think back to part A and think about what that information gives us. So part A, we found that f of negative 1 is equal to 3 over 2. So that means we know that when x is negative 1, y is 1.5. So that means the graph's going to go through a point here. And again, using the symmetric property of the truncus graph, we know then that when x is 3, the y value will also be 1.5. So we certainly don't need to label those points, but it's just a point that we can get our graph to pass through to improve the accuracy of this sketch. So the truncus graph will then just have a shape that looks something like this, and on the other side we'll have a similar shape there. So technically speaking, that's all VCAA required us to sketch. But I'm just going to label the y-intercept here because I'm pretty confident that that is 0 for x and 3 for y. So that's the answer to part 2 of part A for this question. From the examiner's report, we can see that 69% of students got this question fully correct, and 22% got 1 mark out of 2. The examiner's report goes on to say that most students correctly recognised that a truncus shape was required for this question, and that most of these students located it correctly on the grid. Again, curvature was an issue for some, with graphs turning away from the asymptotes or crossing them. So it's important that we sketch these graphs accurately, and we avoid those issues in the future. The examiners go on to say that students who made use of their answer to Part A and found the y-intercept were most successful in producing a correct graph. So even though it didn't ask for those pieces of information to be used, using them helped enormously for students to get that graph correct. The common mistake here was that for those students who did not recognise the need to draw a truncus graph, tended to draw a hyperbola with the correct asymptotes, but obviously the incorrect graph shape. For Part B, it asks us to find the area bounded by the graph of f, the x-axis, the line x equals -1, and the line x equals 0. And I've just copied a version of the graph onto this slide so that we can annotate it, but obviously in an exam you'd be welcome to sketch on top of the graph you'd already drawn in Part A. So that area is bounded by the graph of f and the x-axis, and it's also bounded by the line x equals -1 and x equals 0. So this is the area that they are asking us to find. So that area can be found using a definite integral, and the integral that we'll want to set up is going to be the integral from -1, the lower bound for x, up until 0, for the rule f of x, and I'm going to slightly change this just so that we can apply our rules for anti-differentiation. So I'm going to write this as 2 times x subtract 1 to the power of -2, and that's the same as 2 divided by x minus 1 all squared. And then we still have a plus 1 that we can't forget about there, and we're going to integrate all of that with respect to x. And perhaps one of the more challenging parts of this question is finding the antiderivative of that term that I've just underlined. So I'm just going to come down here and rewrite that, and we can't forget about that plus 1, but I'll deal with that when we get back to our main line of working in a moment. What we're just going to focus in on is 2 times the integral of x minus 1 to the power of -2 with respect to x. And because that 2 is a constant, I can take it out the front. Again, I'll deal with this plus 1 in a minute. And this reveals that we need to use one of the rules on the formula sheet when we have a term that's ax plus b to the power of n. So applying the rule, we're still going to keep the 2 there, and we're still going to have x subtract 1, but now we add 1 to the power, so that will just become -1, and then we divide by the new power, which is -1, and we also technically divide by the coefficient of x, but in this case that's just 1. So that's going to be the antiderivative, and we don't need to worry about our plus c at the moment because it's a definite integral. But if we did just want to clean that up slightly, the 2 will multiply through and go onto the top line. This power of -1 will pull the x take 1 down to the bottom line, so it's going to be 2 over x subtract 1. And we do have a negative on the bottom line, and just to put that somewhere neat, I'm going to put it up the top as a -2. So if we go back up to our main line of working, this can be evaluated as the antiderivative, which we now know is -2 over x subtract 1, plus the antiderivative of 1, which is just plus x, and we evaluate that antiderivative between the same terminals of -1 and 0. Next up, we apply the fundamental theorem of integral calculus to work out this value. So what that means is we're just going to substitute in the upper terminal first. So the upper terminal is 0. So substituting that in, we'll have -2 over 0 subtract 1 plus x, which is going to be plus 0 with 0 substituted in. And then we subtract away from that the antiderivative with the lower terminal substituted in of -1. So we're going to have -2 over -1 minus 1. And then we add x, which is just the same as adding -1 on there. And now our job is just to simplify that as much as possible. So in the first set of brackets, we'd have -2 over -1, which is just 2, and then adding 0 onto that will not change it. And then we'll subtract away from that the second set of brackets, which is going to be -2 over -2, which is +1, and then we still have this -1 there. And then simplifying that, we'll just have 2 subtract, and this second bracket is now 0, so it's just 2, and because it's an area, I'm going to say 2 units squared. So that is the answer to part B of this question. From the examiner's report, we can see that 1/3 of students got that answer correct, and 40% of students managed to get 1 mark. The examiner points out that students were generally able to set up the correct definite integral to represent the area, but often did not find the correct antiderivative or evaluated it incorrectly. So there was mistakes made on finding the antiderivative, and then even if students did get the correct antiderivative, they may have made a mistake when substituting in the upper and lower terminals and evaluating that. The most common errors for this question were antiderivatives that involved a log component, or overlooking the +1 constant when the anti-differentiation was occurring. So that's where the plus x needed to appear in that antiderivative.